In this example, we need to construct a slope field for this differential equation. Now, you'll notice straight away that it's not in the form y dash equals something, so we might need to start by rearranging it. Then we need to look at what type of curve the solution curves seem to be, and check our conjecture by differentiating something we think might be a possible solution curve to see if it actually gives us this differential equation. So to start out, let's just get y dash by itself by subtracting x from both sides, and then we can divide both sides by y. And you'll notice that in the last exercise, this is a differential equation that we've already looked at, so you might even remember the result and it might already be familiar to you. If it's not, that's totally fine. We're building up our skills with each exercise and things should start to connect together. Now, to save myself a bit of time, I have printed out here the table of gradients. Now, let's have a quick look at how we can find all these values. Let me just bring you in close here. Can we actually see this? Good question. Okay, yes, we can just see it, I think. So we are looking at different x values, again from -4 to 4, and different y values from 4 down to -4. And for each of these, we just need to sub them into this equation and say, all right, if x is -4, then we've got -4, that'll just be 4, over 4, and 4 over 4 is 1. So we can see that the gradient for this box will be 1. Similarly here, subbing in x being -3, we've got -3, that's just 3, over 4 gives us 3/4. So I think you can see there that filling in that table is reasonably straightforward, but it's more complicated than the last example because the rows are not all the same, and we do actually need to make the whole grid. Now, when you're learning, making a grid like this is a good idea, and then drawing your solution, your small line segments. Once you get good at this, you might be able to figure out each one and draw it, But the handy thing about making a chart like this is that you can actually see where the numbers seem to line up. So a pattern that I can spot straight away is that I can see, for example, that the gradient is 1 all the way down here on this diagonal, except for this point here, 0, 0. I can also see other gradients that are the same, like there's -1s going down here. So it's a good way to spot patterns, I think. I've also been a little bit cheeky and I've printed out a slope field already drawn for us so that we can have a look at it. Again, I'll bring you in a little bit closer. Now, the process here is just lining up each of these points from your grid and making a line of the right gradient. So we can see very clearly and easily here that these look circles. So our second question, what type of curve do the solution curves seem to be? Well, they look like circles and they look like they've got their center at the origin. So if I was to draw in a solution curve, then I could pick any point, let's say this point here, and draw the solution curve through it, and it looks to be a circle with a radius of 2. I can then draw in other ones around that if I want to. So checking our conjecture that they're all circles by differentiating a possible solution curve, I could say a possible solution curve would be x squared plus y squared equals 4. That would be this one that I've drawn that has a radius of 2. Now differentiating that with respect to x, this term becomes 2x. This term, the 2 needs to come down to give me 2y, but I need to use the chain rule and also multiply by y dash. And differentiating 4 with respect to x just gives me 0. Now I can clearly see here that if I divide all terms by 2, I'm going to get this, and that is in fact the exact same differential equation as we started with. So yes, I can check my conjecture that the solution curves here are circles that have the origin as their center. So we've learnt how to draw a slope field from a given differential equation, but can we identify a differential equation given a slope field? Well, there's a few things that you'd want to look out for. Look out for key points where the gradient might be 0 on your slope field. Consider the gradient in all 4 quadrants. Would it be positive or negative? Because if you've got a differential equation and it's got x and y in it, then depending on whether x and y are positive, only y is positive and x is negative, both are negative, or perhaps x is positive and y is negative, there's going to be some really distinctive gradients that you're expecting to see. You can also consider, once you've narrowed it down using those 2 methods, what the actual gradients are. Are they steep or not so steep as x or as y gets bigger or smaller? Or is it more to do with the distance away from the origin that's determining how steep things are? So here's an example. Which differential equation is represented by this slope field? Let's just bring you in a little bit closer so that you can see it clearly. Now, some key things to look out for. I can see that the line segments are all on a gradient of 0 there when x equals 0 and when y equals 0 at the origin. So x being 0 makes y dash equal to 0. So we can look at these and say, all right, if x was 0, yes, that would make that one possible. Same here, if x was 0, y dash would be 0. Same, if x was 0, y dash would be 0. We can rule out this one then, I think, because here, if x is 0, that doesn't necessarily make y dash 0. So I think we can say it's definitely not that one. I mean, here, y dash would be 0 if x and y was 0 at the origin, which it is, but given that here when x is 0 and y is 1, we wouldn't be getting 0 there. So we've ruled out 1 already. Now let's consider the gradient in all 4 quadrants. So looking up here in the first quadrant, when x and y are both positive, I've got negative gradients everywhere. They're all going that way. So that tells me that, okay, a positive x and a positive y would mean that xy would be positive, but there's a negative sign here. So this looks possible. That's likely. Here, x being positive, squaring it, and a positive y, yep, that's also possible. This one, okay, all right, well, that didn't really rule anything out looking at this quadrant. What about over here in this quadrant? When x is negative and y is positive, we've actually got positive gradients. So let's consider that. X being negative, we'd have negative x, that's just x, multiplied by a positive y, we'd have positive gradients, so yeah, that looks possible for this quadrant. What about here? If x is negative and we square it, it'll be positive, multiplied by positive y, that would give us negative gradients. So it can't be that one. We've ruled it out, because in this quadrant, this differential equation would have negative gradients, and these are clearly positive. So we've narrowed it down. Let's check this one. Negative x values, negative x is just x, multiplied by a positive. Yep, that seems okay. Let's have a look at another quadrant. Take your pick. How about this one? When x is positive and y is negative, we seem to have positive gradients. So let's consider this one. X being positive would mean we've got a negative positive number, so that's negative. Multiplied by a negative, that would give positive gradients. So yep, that seems okay. And this one, x is positive, so a negative positive number, multiplied by a negative squared, that would also give positive gradients. So okay, we're still not ruled out. We need to look at this quadrant, and we can see both x and y are negative here. So a negative times a negative is a positive, multiplied by a negative, that would make it negative, and it is. And here, this would be positive, multiplied by a negative is negative, multiplied by a negative, this would have to be positive. So that we've ruled it out, and we've found the winner. This must be the differential equation that's represented by this slope field. So a bit of a process of elimination sometimes in questions like this, but you can generally narrow it down using these strategies. Now you can also use technology to draw slope fields. I recommend either of these two. The GeoGebra one is super easy to use. Just literally search GeoGebra slope field generator, and up it comes, and you can type in y dash as a formula, and it will just generate your slope field for you. So this might be handy to have beside you when you're working from your textbook. In fact, your textbook even asks you to generate a few of the slope fields using one of these. The Wolfram Alpha one is a little bit tricky to use. The Desmos one is not too bad, but I recommend this one.